Hello everyone. Welcome to my YouTube channel on engineering mathematics. This is my second video on examples on hyperbolic functions. In this video, I will discuss the examples on separation of real and imaginary parts of expressions given in circular and hyperbolic functions. Prerequisite for this video consists of definition of hyperbolic functions, its Euler forms, relationship between circular and hyperbolic functions, and identities of hyperbolic functions. We have already studied this stuff in my previous video. Link of that video is given in the description box. Now let us proceed with examples. First we begin with examples with very low difficulty level. Then gradually I will increase the difficulty level. In this first example, we are asked to separate function sine of x plus iy into real and imaginary parts. This is a circular sine function. So let us begin with solution. Sine of x plus iy can be treated as sine of a plus b. And we know sine of a plus b is sine a cos b plus cos a sine b. So sine of x plus iy can be written as sine x into cos iy plus cos x into sine iy. Now we recall the relation between circular and hyperbolic functions, according to which we know sine ix is equal to I sine hx and cos ix is equal to cos hx. So this cos iy can be written as cos hy and sine iy can be written as I sine hy. So after replacing, we have RHS as sine x cos hy plus I into cos x sine hy. Now you can clearly see that we have separated this function sine of x plus iy into real and imaginary part. I hope you understood this one. Similarly, if you are asked to separate cos of x plus iy into real and imaginary parts, we begin with cos of x plus iy, then we expand it using cos a plus b formula. So we get cos x into cos iy minus sin x into sin iy. Using these same relations, cos iy can be written as cos hy and sin iy can be written as I sin hy. So we get this RHS. Clearly, this is a real part of cos of x plus iy and minus sin x sin hy is imaginary part of cos of x plus iy. Now let us proceed with example number 3. Here we are asked to separate into real and imaginary parts of tan of x plus iy. Let's go for solution. Tan of x plus iy can be written as sin of x plus iy upon cos of x plus iy. Further, to simplify this, we will multiply numerator and denominator by 2 cos of x minus iy. Now this looks like to me 2 sin a into cos b upon 2 cos a cos b. Here I would like to recall formulas of 2 sin a cos b, which is sin a plus b by 2 plus sin a minus b by 2, and 2 cos a cos b, which is cos a plus b by 2 plus cos a minus b by 2. So by using these formulas on this, we get sin 2x plus sin 2iy upon cos 2x plus cos 2iy. You can pause the video and check the calculation. Now further, I will use the relationship between circular and hyperbolic function, which states that sin ix is equal to I sin hx and cos ix is equal to cos hx. So this sin 2iy can be written as I sin h 2y and cos 2iy can be written as cos h 2y. So now it is clearly seen that tan of x plus iy is separated into a real part, which is sin 2x upon cos 2x plus cos h 2y, and imaginary part, which is sin h 2y upon cos 2x plus cos h 2y. I hope you understood this part. Now let us proceed with example number 4. Here we are asked to separate into real and imaginary parts of sin h of x plus iy. Let us see its solution. Sin h of x plus iy can be expanded as sin h of x into cos h of iy plus cos h of x into sin h of iy. Here I would like to recall the relationship between circular and hyperbolic functions, which is sin h of ix is equal to I sin x and cos h of ix is equal to cos x. So this cos h of iy can be written as cos of y, and sin h of iy can be written as I sin y, like this. So clearly this is a real part of sin h of x plus iy, and this is imaginary part of sin h of x plus iy. Similarly, to separate into real and imaginary parts of cos h of x plus iy, we expand cos h of x plus iy as cos hx into cos h iy plus sin hx into sin h iy. Then using these relations, cos h iy can be written as cos y and sin h iy can be written as I sin y. Clearly, cos hx into cos y is real part of cos h of x plus iy, and sin hx into sin y is imaginary part of cos h of x plus iy. I hope you understood this example number 5. Let us proceed for next example. Here we have to separate into real and imaginary parts of tan h of x plus iy. So let us begin with tan h of x plus iy. One can write it as sin h of x plus iy upon cos h of x plus iy. Now I would like you to recall these relations. Sin of ix is equal to I sin hx. Therefore, sin hx is minus I into sin of ix. That means you can convert any hyperbolic sine function into circular sine function in this way. Similarly, cos ix is equal to cos hx. So you can convert any hyperbolic cosine function into circular cosine function in this way. So this sin h of x plus iy can be written as minus I into sin I of x plus iy, and cos h of x plus iy can be written as cos of I into x plus iy. Further, when we take this I inside this bracket, we get minus I sin ix plus I square y, but I square is minus 1, so we get minus y. Similarly, here we get ix minus y. Now we multiply numerator as well as denominator by 2 into cos of ix plus y. So we get expressions of the type 2 sin a cos b upon 2 cos a cos b. Just like in previous example, we have used 2 sin a cos b and 2 cos a cos b's formula. Here also we will use those formulas. So we get minus I as it is into sin a plus b by 2 minus sin a minus b by 2 upon cos a plus b by 2 plus cos a minus b by 2. Further simplification gives us minus I into this sin 2ix can be converted into hyperbolic sine using this identity. So we get I into sin h of 2x, this sin 2y as it is. This circular cosine function can be converted into hyperbolic cosine function using this identity. So this cos of I 2x can be written as cos h 2x, this cos 2y kept as it is. Now when I multiply this minus I inside, we get minus I square, which is 1, minus into minus plus I sin 2y upon this denominator as it is. So here clearly sin h 2x upon cos h 2x plus cos 2y is real part of tan h of x plus iy, and sin 2y upon cos h 2x plus cos 2y is imaginary part of tan h x plus iy. I hope guys you understood how we have separated tan h of x plus iy into its real and imaginary parts. Now let us go ahead for example number 7. Here given that if sine of alpha plus I beta is equal to x plus iy, then we have to prove that x square upon sine square alpha minus y square upon cos square alpha is equal to 1. Let us begin with its solution. Here given that sine of alpha plus I beta is equal to x plus iy, expanding sine of alpha plus I beta, we get sine alpha into cos I beta plus cos alpha into sine I beta is equal to x plus iy as it is. Here we have used sin a plus b formula. Now, using the relation between circular and hyperbolic functions, one can write cos I beta as cos h beta, and one can write sin I beta as sin h beta. So we get sin alpha into cos h beta plus I cos alpha into sin h beta is equal to x plus iy. On left hand side, a real part is sin alpha into cos h beta, and on the other side, real part is x. So after comparing both the sides, we get x is equal to sin alpha into cos h beta. Similarly, here imaginary part is cos alpha sin h beta, and over here imaginary part is y. So cos alpha into sin h beta is y. Now let us take square on both the sides of these equations. So we get sin square alpha into cos h square beta is equal to x square, and cos square alpha into sin h square beta is equal to y square. Further, taking this sin square alpha on the other side, we get cos h square beta is equal to x square upon sin square alpha, and taking this cos square alpha on the other side, we get sin h square beta is equal to y square upon cos square alpha. Now we will substitute values of x square upon sin square alpha and y square upon cos square alpha into LHS of this equation. So we get LHS is equal to cos h square beta minus sin h square beta. But we know that according to the definition of hyperbolic functions, cos h square beta minus sin h square beta is 1. So we get x square upon sin square alpha minus y square upon cos square alpha is equal to 1. Hence, the required statement is proved. I hope guys you understood this example. Now let us proceed with example number 8. Here we are given that if tan of a plus ib is equal to x plus iy, then we have to prove that tan 2a is equal to 2x upon 1 minus x square minus y square, and tan h2b is equal to 2y upon 1 plus x square plus y square. Let us see its solution. Given that tan of a plus ib is equal to x plus iy, then its conjugate can be given as tan of a minus ib is equal to x minus iy. Now let us consider tan of a plus ib plus a minus ib, which is nothing but tan of 2a. Then tan of a plus ib plus a minus ib according to trigonometric identity can be written as tan a plus ib plus tan a minus ib upon 1 minus tan a plus ib into tan of a minus ib. Now let us substitute values of tan of a plus ib and tan of a minus ib from here. So tan of a plus ib we replace by x plus iy, and tan a minus ib we replace by x minus iy. So we get this. Let us simplify this part. When I open these brackets, plus iy and minus iy will get cancelled. So we will left with 2x in the numerator. This can be treated as a plus b into a minus b, which is nothing but a square minus b square, on simplification which we get x square plus y square over here. So tan 2a is 2x upon 1 minus x square plus y square. Similarly, tan of 2ib can be written as tan of a plus ib minus a plus ib. So this can be expanded as tan of a plus ib minus tan of a minus ib upon 1 plus tan of a plus ib into tan of a minus ib. After replacing tan of a plus ib and tan of a minus ib by their values, we get this expression on the right side. Now opening these brackets, we get 2iy in the numerator, and in denominator we will get 1 plus x square plus y square. Further, this left hand side, that is tan of 2ib, can be written into hyperbolic tan function using the relation between circular and hyperbolic functions. So we get on LHS I into tan h2b. That I and this I will get cancelled. So we get tan h2b is equal to 2y upon 1 plus x square plus y square. So guys, we have just proved that tan 2a is equal to 2x upon 1 minus x square minus y square, and tan h2b is equal to 2y upon 1 plus x square plus y square. I hope guys you understood this answer. So let us proceed with example number 9. Here, given that if tan of x plus iy is equal to sine of u plus iv, then we have to prove that sine 2x upon sine h 2y is equal to tan u upon tan hv. Now let us see its solution. Given that tan of x plus iy is equal to sine of u plus iv, now we will separate real and imaginary parts of both sides of this equation. Note that we have already seen the separation into real and imaginary parts of tan of x plus iy and sine of u plus iv. So I will borrow those statements directly over here. So tan of x plus iy can be written as sine 2x upon cos 2x plus cos h 2y plus I into sin h 2y upon cos 2x plus cos h 2y, and sin u plus iv can be written as sin u cos hv plus I into cos u sin hv. Now we compare both sides of this equation for their real and imaginary parts. So after equating real parts, we get sin 2x upon cos 2x plus cos h2y is equal to sin u into cos hv. And after comparing imaginary parts of both sides, we get sin h2y upon cos 2x plus cos h2y is equal to cos u into sin hv. Now we will divide this equation with this equation. So we get sin 2x upon cos 2x plus cos h2y whole divided by sin h2y upon cos 2x plus cos h2y. So this denominator and this denominator will get cancelled. We will left with sin 2x upon sin h2y. On the other side, we will get sin u into cos hv upon cos u into sin hv. But sin u upon cos u is tan u, and cos hv upon sin hv is cot hv. Cot hv can be written as 1 upon tan hv. So we get sin 2x upon sin h2y is equal to tan u upon tan hv as required. I hope guys you understood this solution. Now let us proceed for next and the last example of this video, which is separate into real and imaginary parts of root I raised to root I. Let us see its solution. We focus only on this root I first. So root I can be written as I raised to half. Polar form of I is cos pi by 2 plus I sin pi by 2. Then later using de Moivre's theorem, we will get cos pi by 2 into half, that is cos pi by 4, plus I sin pi by 2 into half, that is I sin pi by 4. But cos pi by 4 and sin pi by 4 both have same value 1 by root 2. So we get 1 by root 2 plus I by root 2. Also note that this root I, that is cos pi by 2 plus I sin pi by 2 raised to half, can be written as e raised to I pi by 2 raised to half. E raised to I pi by 2 is Euler's form for cos pi by 2 plus I sin pi by 2. Then after multiplying these powers, we get e raised to I pi by 4. Now we have two representations for root I. One is 1 by root 2 plus I 1 by root 2, and another one is e raised to I pi by 4. We will substitute these representations in root I raised to root I. So root I raised to root I can be written as e raised to I pi by 4 in this bracket raised to 1 by root 2 plus I 1 by root 2. Now let us multiply these powers. So we get e raised to I pi by 4 root 2 into e raised to I into I pi by 4 root 2. I into I, that is I square, is minus 1. So we get minus pi by 4 root 2. This is like e raised to a minus b. This can be written as e raised to a into e raised to minus b. That is e raised to minus pi by 4 root 2 into e raised to I pi by 4 root 2. E raised to I pi by 4 root 2 can be written as cos pi by 4 root 2 plus I sin pi by 4 root 2. When we multiply this inside the bracket, we get real part as e raised to minus pi by 4 root 2 into cos pi by 4 root 2, and imaginary part as e raised to minus pi by 4 root 2 into sin pi by 4 root 2. This is how we separate real and imaginary parts of root I raised to root I. I hope guys you understood all the 10 examples that I have discussed in this video. In my next video, we will see inverse hyperbolic functions and examples on it. Till then, keep watching my videos. Thank you all of you. Thank you for watching this video. Please subscribe my YouTube channel and press the bell icon to get updates about my new videos.